Uh, Hello everyone. My name is Weichen Tao, and I'm currently a PhD student of Telecom Paris, and my supervisor is Professor Jean-Louis Hourien and Professor Leonardo Lingua-Golosa. Today, I'm going to do a presentation about enhancing networking efficiency with eBPF and XDP technology. Okay, first of all, let's start with the background, the history. Uh, in the in the in the 1990s, as the internet grew quickly, analyzing and managing network traffic become more important. Traditional filtering methods are slow and not very efficient. So in 1992, BPF, we called it Berkeley Packet Filter, was introduced in the BSD operating system as a lightweight way to filter network packet. But I have to say, by the way, BPF was created by Bell Labs, Bravo Bell Labs. The main idea of BPF is to let user write simple filter rules, like only accept a packet from a specific port and run them quickly in the kernel. Later in the 2010s, with the rise of cloud computing, large-scale data center, and performance network, the traditional BPF could no longer meet new demands. Packet processing needed more than just filtering it. It required complex analysis and optimization. System need a more efficient and flexible way to manage and monitoring resources. So in 2014, the Linux community introduced the eBPF, extended the BPF based on BPF. eBPF is no longer limited to network filtering. It has become a much more powerful kernel extension technology, supporting a wide range of use cases I will introduce later. Another significant milestone was in 2016. XDP, Express Data Pipes, is an important application of eBPF, designed specifically for high-performance networking packet processing. It was officially introduced in 2016 with Linux kernel, and XDP is designed for high-performance network packet processing, allowing packet to be handled before they enter the kernel network stack. We will introduce this in following sections. So let's First of all, I want to make a general example. Like if you were a kid, I mean, when we used to be kids, if we don't like a version of a toy we have already bought, um, we can only throw it away or wait for a new version to be released. For example, I bought a transformer and I wanted the transformers with a sword. So, or maybe I can wait for the toy company to release official components. But Lego allows us to customize our new toy by continuously adding bricks to the main structure or modifying existing one. So eBPF technology is like Lego bricks. It allows you to continuously add eBPF program to enhance the functionality of the kernel. Before eBPF, when we want to add and run user customized program in the system, there were normally two approaches. One was modifying the kernel source code, but this required recompiling the kernel source code and rebooting the system, making debugging cumbersome. So it could also introduce security problem or system instability. So another approach was using kernel modules, but they also pose the security risks, as error could lead to system crashes, and the threshold for the developer is really high. And for the kernel module, everything happens in the kernel, so it's not very easy. It's kind of difficult for debugging. But eBPF, extended Berkeley Packet Filter, this technology allowed us use customized program to run inside the Linux kernel without modifying the source code or loading new kernel module. It provides us a safer and more efficient way to extend the kernel functionality. You just need to write a simple program in language C and attach it to the kernel, just like assembling Lego bricks. So how does eBPF works? Let's say let's say this figure. Computer, we always say that computer basically run code, right? So, well, eBPF, I think it's like a virtual machine inside the Linux kernel that runs special eBPF bytecode. You can see in the figure, the yellow, the yellow part is the eBPF. It's like a virtual machine. But how does it actually works? Let's break it down step by step. I think first, you write a eBPF program. You can use C language or eBPF assembly, whatever you want, you are comfortable with. Then you compile it into eBPF bytecode using the ILVM clone compiler. Next, you need to load you need to load this bytecode into the kernel. You do this with a system call, whose name is BPF. Once the bytecode enters the kernel doesn't just run it right away. It first check if it's safe or not. It will make sure there are no infinite loops, that memory is accessed properly, and that the program won't crash the system. If everything looks good, the kernel JIT compiles the eBPF bytecode into native machine code, so it run even faster. So now, where uh, where does this program actually run? Inside the kernel, actually, there are many specific points. We call it hook points. The eBPF program will be connected to these hook points. These hooks are like some checkpoints. Whenever the kernel reaches one, uh, the attached eBPF program automatically runs. So for example, if you are monitoring a network traffic, you can attach an eBPF program to the network stack. Every time a packet arrives, your program can analyze, modify, or even drop it before it reaches the application. So so now it's the whole processing of a eBPF program how the eBPF how a eBPF program runs. Now, what if your program needs to store or process data? Uh, that's where eBPF maps come in, actually. You can see here the eBPF map. Think of the eBPF map like a built-in key-value database inside the kernel. Your eBPF program can save data, read data, and update information in real time, making it perfect for things like traffic filtering, system monitoring, or performance tracking. Every eBPF program can save data in the eBPF maps, and we can read it in user space. I mean, in the user space, some user program or another eBPF program can read the eBPF map at the meantime too. So, uh, I think is the best part. User space program can access the data. So by calling the BPF system call, they can interact with the eBPF maps, like we can retrieve some information and even send commands back to the eBPF program. So in simple terms, eBPF lets you run custom programs inside the Linux kernel without modifying the kernel itself. It's safe and flexible and fast, making it super useful for networking security, performance monitoring, and more. It's like adding a custom feature to the Linux kernel without breaking anything. So let's look at some details. How does the BPF system call do? Works. The code on the right is the definition of the eBPF system call in the Linux kernel source code. Essentially, it's a switch case. You can see that it's a switch case structure that handles different instructions. This instruction these instructions include loading eBPF program, like this one, and operating on maps. Like you can add, delete, query, and update the data in the maps. Other functions like, for example, attaching or detaching eBPF program and managing objects, there is also some function like that. So you can think of BPF, the system call here, the BPF system call here, uh, is the key part of eBPF. It's the only way that we can interact with eBPF in the kernel, making it an essential tool for working with eBPF program. And another thing is about the hooks in eBPF. The type of hook you can use to deter the the type of the hook point you use determines the kind of eBPF program you can write. There are several different types of hooks. First, there are static tracing. This use some trace point. This use the trace point, which are fixed hook points predefined by Linux kernel developer. They expose useful runtime information like when a kernel function is called, memory allocation, or a file system operation. Static tracing is stable, efficient, and perfect for tracing well-defined events. Next, we have dynamic tracing, which use the kprop. Kprop is another very important Linux kernel mechanism. This is much more flexible because you can add hooks to almost any kernel function in the instructions when the system is running. Unlike the trace point, you are not limited to predefined hooks. The downside is that there is more, um, I mean, the it's more resource intensive and is greater for, but it's greater for debugging or monitoring specific behaviors. So finally, there is a sampling like a perf event. This BPF prog type of perf event. This is used for performance monitoring. It can sampling things like the CPU circuits, the cache misses, or other hardware counters. It's perfect for profiling and analyze the system performance. So, so why does this matters? Different hooks allows you to write different types of eBPF program, each suited to the specific task. So static tracing is greater for common events. Dynamic tracing gives you more flexibility to debug or monitor specific actions, and the sampling is ideal for performance analysis. So this variety is what makes eBPF so powerful and flexible. So the another important thing is about the eBPF maps. eBPF maps has a different is a powerful, efficient way to store and exchange data, and not only between the eBPF program and the user space application, but also between different eBPF programs. They support various types to suit various use cases. For example, the array map is a great for fixed size data, and the hash map allows you to store key value pairs for quick lookups. And there are also LRU hash map automatically remove the latest used entries when the maps is full. So these maps make it easy to track runtime data, monitoring performance, and maybe we can implement customer logic in eBPF programs. So there are also some other key infrastructure that make eBPF such a powerful technology. So the first is eBPF map we have talked before, and the next we have also eBPF help functions. There are predefined function in the kernel that the eBPF program can call to perform specific operation. For example, you can use BPF skip load bets to load bets from a network packet, or BPF map lookup element to retrieve data from a map. We have seen it before in the eBPF map. And even BPF K-time get NS to get the timestamps for performance monitoring. This helper allows eBPF program to interact with the system in a powerful yet safe way. Finally, let's talk about the telcos. Uh, Telcos actually it allows one eBPF program to jump directly to another program at the end of its execution. Why is this useful? It helps break down the complex logic into smaller reusable pieces, making your eBPF program more modular and easier to manage. But there are another key reason why telcos are useful. This brings us to the limitation of eBPF. Uh, eBPF has a lot of eBPF does come with some limitations that we need to be aware of. First, there is a limit on the number of the instructions. eBPF programs are capped at a maximum of 4,096 instructions per program. This ensures if safety and efficiency, but it can be challenging when we're trying to implement very complex logic. So telco, I mean, the telco we say before, telco is a very great way to mitigate this limitation. We can use telco to chain multiple eBPF programs together, allowing us to implement more complex logic and functionality. So there is also another limit is on telcos. You can see in this here. Telcos allow eBPF programs to jump to another, but the maximum depth is restricted to 32 cores. So this keeps the program execution predictable. And also eBPF program has memory usage limit and also has eBPF used a very restricted instruction set. This restriction ensures programs are safe um, and verifiable, but it means certain operations like the floating point arithmetic are not supported. So finally, eBPF is a event-driven and highly dependent on the hooks. Programs can only run in response to specific kernel events or hooks, such as the trace point or the kprop. This means eBPF program cannot execute independently or on its own schedule. So I think understanding this constraint um, can help us to design better and more efficient solution with eBPF technology. So I think I want to show you some example of eBPF. Uh, sorry, wait a moment. I want to show you some example with eBPF here.
Oui, entrez. Bonjour.
Est-ce que tu penses qu'on peut parler en
Ok.
30 minutes
Oui.
Cet après-midi, je suis au cours de Bartec, donc je serai pas là.
Ah, d'accord.
T'as une
Euh,
conférence
Là, j'écoute un truc, mais
Oui, oui,
ça me passionne pas, donc on peut discuter. Mais
voilà.
Okay, could I continue?
Yes.
Okay, sorry.
Atelier.
Okay, so because now I'm in China, so I could not use my server at Telecom Paris very, I mean, fast. So I want to show you this example with my local virtual machine. I'm going to use SSH to connect the two virtual machine. Okay, so currently I have let me think. Yeah, I have two virtual machine now. Okay. Now I have two virtual machine, which name is Ubuntu 01 and Ubuntu 02. Um, I want to use eBPF. I want to use one eBPF function in on the Ubuntu 01. I'm going to show you here. Okay, so here you can see the libbpf bootstraps. Actually, it's a starter kit. The bootstrap libbpf starter strip is a starter kit for eBPF developer. And here in it, you can see the BCC dictionary. In the BCC, actually, you can imagine it like a developer environment, just like the Visual Code Studio is for the user is for the eBPF developer writing, load, and running eBPF program in the kernel. In the BCC, you can see a lot of example and BPF tools. So I want to show you one tools. I want to show you one tool in it. Yes, this one, func latency. I mean, sometimes like when you are in a company, you want to treat, there is some problem in the connection, and you want to find the bottleneck. Why is the connection is not so, is it's so the latency is so high? So maybe you want a function you want a tools help you to find which function has a very normal latency. So the function latency here, the tool is help us to get the latency of the Linux kernel functions. Like here, it's very easy to run it. I just need to do func latency. Yeah. Yeah. Okay. Yeah. Sorry, I forgot one argument. If I want to use this function, I need to give him give its arguments that which function I want to listen. For example, if there is a very oh wait for CPU wait for uh receive RCV. Yeah. TCP wait4 RCV is a very important kernel function in the in the network stack. For every TCP connection, the TCP wait4 receive function will be called. So I will use this tool, the function latency, to help me to to calculate, not calculate, yes, to calculate the latency of each time I called this function. So okay, the program is okay, the tool is running. Now I need to open another net, another session for the service one. Okay. So now I want to build a TCP and I want to build a TCP connection between the service one and service two. I will use eBPF 3. eBPF 3 will generate some traffic could generate some traffic between two server. So I will make the first server, the Ubuntu 01, which we have run the eBPF program as the server, and another one, another virtual machine as the uh sorry, eBPF 3. Yeah, another virtual machine as the traffic generator. I mean the traffic sender. So now I run it. You can see that the Ubuntu 01 is sending the traffic to the TCP traffic to the Ubuntu 01. Yeah, and now it finished. Let's go back to our eBPF program. I end this program. Okay. So now you can see here in this you can see this figure. This figure has you can see how to say it provides us a distribution of the latency of the TCP wait4 receive functions execution. Sometimes before when I use it, I found sometimes the latency will be really for example here the latency of will be really high, and maybe it's because this function there's some problem with this function, and you can find sometimes the distribution in the when the latency is really high, there is some sorry, I'm kind of nervous. Um, But anyway, these tools help provide us a distribution of the latency of this function execution. This is the first example, and here I have another. Oh, sorry. I'm going to share. Yeah. Uh. Oh, sorry. Wait a moment. Okay. Uh. Okay. So this is the first example, and I intended to show you guys another example, but maybe there is a time limitation. Because I have another things to introduce is XDP. So maybe I want to talk about XDP, and if we have time, I will come back to this example. So now let's talk about XDP, the Express Data Path, and let's start with the background. Um, so with the rise of the NFV and the SDN technology, the traditional network equipment like the routers and the switches have been gradually moving to software. So running on that means they are running on general purpose servers. This shift relies heavily on the kernels to handle network data processing. But however, the Linux kernel was originally designed for general purpose use, not for high performance network processing or specialized network functions. So it doesn't handle this job very well. Uh, the complex network protocol stack in Linux in Linux kernel is a key factor causing kernel performance bottleneck. You can see in this picture that every packet goes through the Linux kernel. It has to pass to the complex network stack. So that's mean each layer there are multiple layer of processing, and each layer adding the overhead and making it the entire process inefficient. So over the past decade, over the past 10 years or 20 years, the network performance optimization, I think, has primarily focused on bypassing the network protocol stack with the solution like the DPDK, the NetMap, and later the XDP. So XDP is a specialized type of eBPF program. Or we can say that it's a special hook point located at the earliest stage of the network stack within the network driver. Its goal is to process packet as efficient as possible, even before they reach the kernel's networking stack. With XDP, packet can be dropped, modified, redirected, or to another device, or just let it pass. So, for example, if a packet is malicious or unwanted, XDP can drop it immediately, saving the system resources. So by processing the packet so early, it avoids the overhead of the full network stack, making it perfect for the task like the DDoS mitigation, uh, the load balancer, and the packet filtering. A DDoS attack that can send. I'm not sure that if you guys know the principle of the DDoS. A DDoS attack is sends a massive number of requests to the target system. It will exhausting the system, the server's resources, and congesting the network, making it unavailable to real user. But with XDP, we can block and drop DDoS traffic right at the network driver, stop it before it reaches the kernel and the network stack, making defense much more efficient. So another is another picture, I mean figure. I want to do a comparison between the DPDK and the XDP. So strictly speaking, I think XDP is not a typical kernel bypass technology because it does bypass the traditional Linux network stack to achieve more efficient packet processing. It can be considered partial kernel bypass since it still operates in kernel space. But in constraint, DPDK fully bypass the kernel with all packet processing done entirely in user space. We must acknowledge that when it comes to raw packet processing performance, DPDK outperforms XDP because DPDK everything is running in the user space, and DPDK is an independent, and the DPDK requires a dedicated CPU for CPU core for the pooling. Yeah, but however, DPDK is an independent application, but XDP is integrated into the kernel, making it much easier to deploy. So I think because of this, XDP still has a wide range of use cases, offering a balance between the performance, the efficiency, and easy to deploy of deployment. So here I want to show you another example of XDP. It will be much more clear and easy to see. Sorry. Okay. Um, yes, here. Um, okay. So again, we still are these two server, the Ubuntu 01 and Ubuntu 002. I'm mainly working on Ubuntu 01 because I will load some XDP program on it. How to hide this one? Sorry, wait a moment. Click on. Yeah. Okay. So let's go back to to let's go. Yeah. Okay. So the first thing is about the XDP tutorial. Uh, you can find this tutorial in the on GitHub. Actually, it's kind of something like same as the BCC is a working environment for for XDP developer. It provides us an environment to write and running and compile and load the XDP program. So in the XDP tutorial, you can see many examples. I'm going to show you one basic example and later a more complex one. So here in the basic basic 01 XDP path, you can see one XDP program which name is XDP path XDP path kernel and XDP path user. First, you just need to focus on this one, XDP path kernel.c, because this one is the core program of the XDP program. It's in the kernel, not in the user space. So let's check what written in it. It's very simple. Actually, there is just one action. For each packet, just return XDP drop. XDP drop is XDP instructions. It just means that drop everything you receive. Actually, before I modified it, here is return XDP path because the name of the program is XDP path kernel. That means every packet arrives in the kernel. This program will be executed, but it will do nothing because every packet will be passed. But now I modify it to XDP drop. That means every packet will be drop. So let's check how now what I'm going to do is to load this program on the kernel. Okay, so sudo I'm going to use IP link. If we want to load a XDP program on the driver on the hook, we first of all we can use the IP link to wait a moment. Set device S33 object XDP pass kernel once 10 XDP object. Sorry. Sudo IP. Yeah. Uh, um, BJ. Wait a moment. I forgot the way I used with the IP link because actually normal I want when I want to load a XDP program I will use another tools like which name is XDP loader. But here in my virtual machine I didn't install the XDP loader, so maybe I will check the IP link set device XDP. Oh yeah, I forgot one XDP. Sorry. Here XDP prop object file doesn't contain stack prog. Oh, XDP. Sorry. XDP. Oh, yeah. I forgot another parameters. Yeah. After this command, I have loaded this XDP program on my driver. I mean on the hook point. Now every packet arrive in the driver on it reaches the hook points. This program will be executed. So let's check if it has been successful load on it. Eh? Sorry, it doesn't work. Yeah, sorry. The reason that it doesn't work because now I connected my virtual machine with the SSH. So if I dropped every packet on the driver, that means SSH connection will not work again. So let's go back to the Ubuntu the virtual machine and check let's check with the IP link. You can see that when I enter IP link on my on my net card ENS33, you can see one XDP here, prog/SDP ID 115.5. This means that my XDP program has been attached on this net card, and that's why my SSH connection here doesn't work anymore because every packet it receives will be dropped. It executes the XDP dropped actions. So how could I remove it? It's just another command. If I use IP link, I mean, I just use IP link sudo IP link set device. I will indicate the driver, the network card, ENS, and then XDP off. With this command, if we enter IP link again, you will see that the XDP program has been removed. You cannot see the prog XDP anymore on here. So let's go back. So let me check if I can use the SSH with the Ubuntu with the virtual machine. Yeah, we can use the SSH connection again. So here is a very simple example of the XDP program. Actually, I prepare another more interesting example for you. It's a XDP based ACL. It's a more complex one. Here. Yes, this one is okay. So let's go back to the Ubuntu 01, our main virtual machine. Here is another dictionary which name is XACL, and and the XACL is a XDP based ACL. I mean a firewall, but it's a very lightweight and a simple firewall. I write it by myself, and in the XACL you can see that CD XACL core. There is a lot of here is if I want to run this ACL, I have to do many things before. But before that, I want to show you the infrastructure here. Yeah. Okay. So for each XDP program, we know that XDP program is will be attached on the driver. I mean in the kernel space, and my main ACL program is being attached on the driver. Its name is XDP kernel prog, and every packet passing the program will be checked if there is some rules to drop it or just let it pass. This is the first thing, and the second thing is that I have read some rules. I have some rules, and I need to load these rules into the eBPF maps, and then these rules will be used by the XDP kernel program through the eBPF maps. And the third thing is about I write another user space program to check how many packet I have refused and how many packet I how many packet have passed. So let's go back to the server. That okay. Now, first of all, I want to load my kernel space program on the driver. First, I need to do is load. Uh, do yeah. Do I just need to run this XDP loader program, and I have to assign some parameters like the device. Device is the name of my network card. After that, you can see that the BPF the BPF program the eBPF program has been loaded. Actually, it's the XDP program. And now let me check TP link. IP link. Yeah, you can see the XDP program has been attached. And then I want to show another thing is about the rules. Where I put all the rules, it's in the config. It's here. It's in the config.d. So let's go into it. And you can see here is a blacklist and a whitelist. And then let me show you the blacklist. You can see there are the three elements. The second element is like it will deny every ICMP request. We know that ping command will send ICMP request to another server. So if this ACL will deny every ping request, that means I cannot use my second server to ping the first server. So what I need to do next is to load this rules on the eBPF map. So what I need to do is just to run the XACL admin ACL admin. This program will help me to load the rules to load these rules on the eBPF map. And you can see sorry, a moment. Sorry, my computer is kind of lock. Yeah, okay. After that, uh, yeah, with this command, I will load every rules on the eBPF maps. Let me check. What command? Oh, what's the problem with it? Ah, oh yeah, maybe CCL. One moment. XACL. Ah, okay. I config one deep, one black. Yeah. Back address. XACL load ENS. Yeah. Okay. You can see that 3 rows has been loaded. That means I have loaded this rows on the eBPF map, and then I just need to check if I can ping this server. Ping. Yeah. Now I cannot ping it anymore. But at the meantime, if I run another if I run the XDP sudo .0 XDP states SFMD sorry, you can see that uh during the time that I add the XDP program, it has received around 18 packet, and after I load the rules, there are several packet has been dropped directly. That means the ACL works. And if now if I remove the XDP program, you will see that you can see the changes. IP link set device 33 XDP off. Okay, when I remove the XDP program, when I remove the XDP program of the ACL, you can see I can ping the server from another server. So, uh, I'm sorry, I'm not. There is some problem with my. I am not very. So there is some problem with my presentation here, when I show you the example. But I hope that I have explained clearly what XDP is, what eBPF and XDP technology is, and what we can do with it. And if you have more question on it, feel free to ask me.